Right. This video is answering some of the 11.2 pH, or not pH, 11, yeah, the 11.2 pH questions. A lot of them were about acids and bases and how to determine acids and bases. I made a list of the common questions and a couple interesting ones. And so I'm going to try to hurry and quickly go over this. So what makes things acids or bases? Is everything classified as an acid or base? First of all, what we're worrying about, the two definitions we are working on, it's basically hydrogens, a hydrogen moving from one chemical to another chemical. So it's the protons transfer that makes something an acid or a base, whether it gives away a proton or whether it accepts a proton. And that is your basic Bronsted-Lowry acid and base definition. Now, somebody asked, okay, is everything classified as an acid or base? No, because not everything is giving away a proton and not everything accepts protons. So acids and bases are only those things, those types of chemicals. So what is the difference between Arrhenius acids and the Bronsted-Lowry acids and bases? Now, for an Arrhenius acid is something that has H at the beginning of the acid. Now, this is not a minus, this is it's attached to something, okay? So that's what that is. Such as like HCl or HBr, that's what that represents. And so you have something that starts with an H, and an Arrhenius base is anything that ends with OH. Okay, so that's how we can tell an Arrhenius acid or an Arrhenius base. So this is your Arrhenius acid. I'm not going to spell Arrhenius, okay, because it will take too long writing with the mouse. So this is your Arrhenius acid, and this is the Arrhenius base. I need to slow down for Google to keep up. Okay, so that is your Arrhenius base. Anything that ends in OH is your Arrhenius base. Anything that starts with an H is an Arrhenius acid. Okay, now we've also got our Bronsted-Lowry, and I'm abbreviating it BL. Okay, this is taking a long time. I apologize. So we've got Bronsted-Lowry acids and bases. So your Bronsted-Lowry, your acid, okay, now I'm gonna, okay, so your Bronsted-Lowry acid is your proton donator, okay? So in the reactant, on the reactant side of your equation, which of the chemicals has the proton on the reactant side but does not have that extra proton on the product side? Okay, that is your Bronsted-Lowry acid. Then you have your Bronsted-Lowry base. Okay, and your Bronsted-Lowry base, that's the proton acceptor. So which of the two chemicals on the reactant side has the or does not have that extra proton, but on the product side, it does have that extra hydrogen. Remember, a proton, we'll say proton or hydrogen. So the hydrogen ion. We use both terms interchangeably. So the acid has the proton on the reactant side, but doesn't on the product side. And the base does not have the proton on the reactant side, but does have it on the product side. Okay? Is that all right? So when we look at the conjugates, so your conjugate acid and base, I'm not going to write out conjugate, I'm just going to write out CONJ. Okay? Your conjugate base is paired with your acid. So you have an acid conjugate base pair. Okay? So those two get paired together. So on your reactant side, the acid has the proton. On the product side, the conjugate base does not have the proton. Your base conjugate acid pair that means that on the reactant side, your base does not have the proton, but on the product side, the conjugate acid now has that proton. Okay, let's look at, we were going to do these in class, but look at these examples. So right here, let's decide what is the conjugate acid, what's the conjugate base, or what's the acid, what's the base. So if I look at my two chemicals, okay, this is acetic acid, and water gives me the acetate ion and a hydronium ion. If you look carefully, this has, if you count your H's, this has 4 H's on the reactant side, but it's only got 3 H's on the product side. That makes, this is your acid. Okay, let's see. I am going to, okay, that's the acid. This is your conjugate base. Okay, so these two are paired together. And then your water molecule here, we're going to make it blue. Okay, the water molecule is the base because over here on my product side, it now has this, it has the extra hydrogen. So this is your base. Okay, this is your conjugate acid. Now notice if I reverse this reaction, the hydrogen in this hydronium ion is going to go back to the acetic acid, which means that these two compounds will continue to fluctuate back and forth at equilibrium between, this will go from being acetic acid to the acetate ion, and this will go from being neutral water to a hydronium ion. Okay, let's look at this one. This, you've got your HSO4 ion and a hydroxide ion. On the product side, we have water and we have the sulfate ion. So if I look here, my H is going from the sulfate to the water. But that means that I have, this is my acid because over here, the sulfate ion doesn't have the H. So this is that is my acid, and this is my conjugate base. So these two are paired together. On the reactant side, this is my base. We'll go back to blue. That's my base. And over here, water is my conjugate acid. Okay, so base, acid, or base, conjugate acid, acid, conjugate base. Just up here, like this one, this is my acid, conjugate base. This is my base and my conjugate acid. Okay, I hope that helps with the conjugate acids and bases. Because I had a lot of questions about conjugate acids and bases. Okay, let's go to this next question. Do we need to know the water self-ionizing reaction? Okay, so the water self-ionizing reaction is H2O. So our neutral water is at equilibrium, and it can produce an H3O plus, or in other words, a hydrogen ion. Okay, remember these two are the same, plus a hydroxide ion. Okay, this is the ionizing reaction, or you'll also probably hear it called in some of the other videos, the autoionization. Water will perform, it's going through this process all the time. It is autoionizing. So it breaks apart. Notice how water can either donate a hydrogen or it can accept a hydrogen. That's where we get the hydronium ions, because the H plus is picked up by another water molecule. That's where the hydronium ion comes in. Okay. So I hope that explains why water is both an acid. It can act as an acid and a base, because it can both donate a proton and it can accept a proton. So it's both a donator and an acceptor. So it acts as a Bronsted-Lowry acid and base. The equilibrium constant, K. So if you watch the other video, the estimating and calculating pH and OH video, I talk a little bit about the equilibrium constant of water. That means, well, the equilibrium constant of water, this equation right here, totally covers the equilibrium constant of water. That means that the concentration of my hydronium and the concentration of my hydroxide ions are the same, okay? And we always have a concentration of 1.0 times 10 to the negative 14th. Okay, and K, just a capital K, means equilibrium constant. If there is a W down here, that's the equilibrium constant of water. There are several equilibrium constants. Every equilibrium reaction has an equilibrium constant. The only one you have to know and remember is the equilibrium constant of water, which is 1.0 times 10 to the negative 14th. So that your hydroxide ion concentration and your hydrogen ion concentration, when you multiply those two together, you get 1 times 10 to the negative 14th. Okay. Let me erase this. Yes, I found a better way to erase it. I got several questions about, can a pH be higher than 14 or lower than 1? Yes, there are things out there called superacids and super bases, which do have pHs. You can have a pH in the negative range, which is not the actual scale that they use, but they can estimate and kind of equate it to the pH scale, because most people understand the pH scale much better than they do the other scale. So we can have, there are 2 big superacids. I'm trying to remember what both of them are called. Anyways, one of them is has a pH of negative 18, and the other one has a pH of approximately negative 31, which is extremely strong. And by the way, that second one can only be stored in something that is coated in Teflon. It will eat through everything else. Just thought you might want to know that. If you want to know more about them, Google it. Do some research, learn about it. They're actually really interesting. There's some really cool YouTube videos with somebody using those acids. What numbers on the pH scale are bases? Okay, so if we've got a pH scale, it is linear. Right here is 7. Okay, and 7 is neutral. Water is neutral because that means that my hydrogen ion concentration equals my hydroxide ion concentration. Okay, that's when something is neutral, is when those 2 concentrations equal each other. Now we go down here, we start at 1. I'll slow down a little bit, but then we have 2, 3, 4, 5, 6, 7, and then up here we have 14, and then we have 8, 9, 10, 11, 12, 13, 14. Okay, so my scale's not very even. This side of my scale are your acids. Anything within the range of a pH of 1 to 7 are acids. Anything from 7 to 14 is a base. Okay? So if you've got anything with a pH above 7, it's a base. Anything below 7 is an acid. Everything in between is neutral. Okay? Or if it equals 7, it's neutral. All right? So if you watch the other video, somebody's asked, I'm still confused on how to tell if a solution is neutral, acidic, or basic. If you are given the concentration, the hydrogen ion concentration of a solution, if you watch the other video, I teach you how to estimate the pH using just the concentration. You can figure out if it's acidic, if it's basic, or if it's neutral by estimating the pH by looking at the concentration. So I suggest you look at that video, and it will help you to determine, if your estimated pH is between 1 and 7, or if it is between 7 and 14, and that will help you know if it is an acid, a base, or if it's neutral. So I think I already kind of answered this one. What's a logarithmic scale? Well, let me continue this. Each one of these little steps here on the pH scale is a factor of 10. Okay? So each one of those is a times 10. So if I am going from a pH of 1 to, let's say that would be 4. Okay, whoops, here we go. Okay, so I'm jumping from 1, 2, 3 to 4. Okay, each one of these steps is times 10. So pH of 1 has 10 times the number of hydrogen ions in it as a pH of 2. A pH of 3, pH of 1 has 100 times the number of hydrogen ions in the solution as a pH of 3. So if I go all the way to 4, that is 3 jumps. So it is 10 to the third power. So 10 times 10 times 10, which equals 1,000. Okay. My equals won't, yeah, okay, it won't stay. So something with a pH of 1 has 1,000 times more hydrogen ions in it than something with a pH of 4. Okay. So remember, on the acid side of your okay, we've got more H plus ions on this side. Sorry, I can't get it to write more. So I've got more H plus ions on this side, and on this side I have more OH ions. Okay, then I have hydrogen ions. Okay, all right. So yes, I highly recommend you watch the calculating pH video, especially since there's some information on there. Add it to your notes. It will help you with the quiz. Okay, and somebody asked, why are all the pHs in our body except for our belly the same? First of all, our stomach acid, our stomach has to break down the food. So we have to have the acidic stomach acid in order to break our food down so that we can digest it, because our body cannot take the big chunks, those big molecules that are all together. It can't pull the nutrients that we need out of those big chunks. So they've got to be broken down into the individual molecules. And the rest of our body, we have to keep it at a pH approximately, our bodies are a tiny bit basic because the pH of blood is 7.4. And that's about where our bodies should stay, because if our bodies are not neutral, then whether it's acidic or basic, it will start taking hydrogens off of the molecules that make up our cells, that make up our DNA, and it will start breaking them down. We will, basically kind of start dissolving. Okay. One last question that somebody asked that I probably will answer. I've had a couple people ask this. On the notes, there are two properties of acids and bases that are shared. The first one is that they dissolve in water. Okay, they dissociate in water. So they become their ions in water. The other one is that they burn. Okay, both acids and bases will burn you. They will burn skin. They will eat through your skin if we are not careful. That's one of the reasons why we do things I do things in the lab the way that I do them. Okay, so those are the two shared properties of acids and bases. I hope this helped. If I did not answer your question for this section, please please email me and I will do my best to email you back. I think I've been doing pretty good about responding to emails. And I will help you. I will try to answer your question via email. I am also going to start some Zoom meetings, and hopefully some of you can join the Zoom meetings. I will send out an email on that probably this afternoon. Okay, good luck, guys. You guys are doing awesome so far with this at-home learning. I will hopefully see some of you on a Zoom meeting.